All right, so first question is honestly pretty simple. If you know your polyatomic ions and you know your ions, you should be in great shape, okay? So let's go over number one together. So it tells you that a saturated solution of sodium phosphate right here has a concentration, sodium concentration of 0.3 molarity. So if you notice, if you remember these brackets, they mean concentration. This is molarity, so molarity is moles over liters. And then it's asking what is specifically the molar solubility of Na3PO4. So basically what it's saying is that you have a solution of Na3PO4, and it tells you in here the concentration of Na plus is 0.3 molar. Now, if you look at this, this is an ionic compound. Okay, if you put an ionic compound in water, what does it do? It dissolves, right? And so it's going to dissolve into the ions it's made out of. So can somebody give me one of the ions that this turns into? Yeah, PO4. PO4 3 minus, and if you remember the name is phosphate, because I know that everybody knows their polyatomics, right? Been making this joke since like October, but anyway. And then what's the other ion it turns into? Na. But how many NAs does it break into? 3. So you're going to get 3 NAs.
Like 3 compounds?
Yeah, 3 individual NAs. So one of this turns into 3 NAs and 1 PO4. Okay, so that's why it's important to know your ions. It's because you know what it breaks down to. Because it tells you your sodium, the Na concentration is 0.3. So how would we find the concentration of the entire ionic compound? So there's 3 of these, and that's 0.3, not times 3, because you're going the other way. You're dividing it by 3. Yeah, because Na is 0.3, so Na3PO4 is 0.1. So your answer is going to be A. Okay? So this kind of got messy, so let me just make it a little bit more clear. So when we put Na3PO4 inside of water, it turns into 3 Na pluses and 1 PO4 3 minus. Everybody good with that?
Yes.
Okay. It tells you in the problem that Na by itself is 0.3 molarity. And it's asking what is the molarity of sodium phosphate. Well, 1 turns into 3, and if you look here, right, if you want to go backwards, you just divide by 3, so it'll be 0.1. Okay. Okay, so for number 2, how many of you guys put C? Okay, or thought C? Yeah, so C seems like the logical choice, but C is actually incorrect. Okay, so yeah, that's why I front-loaded a lot of like prep telling you there's a term. So let's talk about it. So C is incorrect, but let's talk about why. So you guys probably saw the temperature increases, right? And so you're like, oh, that means it's exothermic. It's going to release energy, right? So I'd say that's probably the second best answer. But when you look at the term, it says you are breaking the bonds between lithium and chloride, where here is saying that you're dissolving. Well, let's just think about it. We talked about in the previous problem that when you put an ionic compound inside of water, what you're doing is you're dissolving it, right? So it turns into Li plus and Cl minus. Okay, so when you look at this solution, we still call it a lithium chloride solution, right? So what you're doing is you're not breaking the bonds, because they are still the same compound in the solution. We call this dissociation, right? And so that is the term that kind of makes this answer not fully correct, right? And so the answer is actually not going to be C. Okay. So let's look at the other options and go through them together. So here it tells you the intermolecular strength between water molecules is stronger than the bond energy within the LiCl lattice. So this answer is actually incorrect, because when we look at a ionic compound, we know that they are organized like this, right? They're organized, the positive and the negative ions, they're organized like this. And this answer is saying that the forces between the water molecules. So we got water molecules that are gonna come into contact with it, but option A is talking about the forces in between the water molecules, not the relationship between the water molecules and the actual ionic compound. So this has nothing to do with what's happening with dissolving in the water. Okay, so A is going to be incorrect. Yeah. Lattice is like this crystal structure, this alternating positive negative structure. That's what we call a lattice.
Just describing the compound.
Correct, yeah. It's just like the shape that it makes. Yeah, great question. And then here it says attraction of the lithium ions to the negative dipoles in water is weaker than the attraction of chloride ions to the positive dipoles in water. So basically what it's saying is that this attraction between Li, I don't got a Li in a good, Li is right here. So it's saying that it's comparing this connection, sorry, this is Li by the way, you can't tell. Li, it's saying that this connection right here is weaker than this connection right here. Well, this question doesn't give us any information about that, right? Because we know it's going to dissolve anyway. So this doesn't have anything to do with that. So B is actually incorrect. And so your answer is going to be D, by process of elimination. But let's also talk about why it is D, okay? Because if you look at D, it says the strength of the ion dipole attractions exceed the lattice energy. So you're comparing the ion dipole interactions with lattice. So let's look at the definitions. Ion dipole is between these ions and the dipole caused by the water, right? It's saying that this is stronger than the connection between the ions, which we know is true, right? Because that's why it dissolves in water to begin with. It's because this intermolecular force is stronger than this force right here. So the answer is going to be D. Okay? Yeah. It is being recorded, yes. Yeah, so kind of a tricky question. If you put C, then honestly, that's not too bad. You know your terms pretty well. It's just that D is the more correct answer. Okay? Yes.
Why not C again?
C, because we're talking about dissolving, not breaking the bond. It's still considered a lithium chloride solution, so we wouldn't define it as breaking the bonds between them. Yeah. Alrighty, let's move on to 3, which is titration. You guys probably love doing titration on your own, right?
No.
Okay, probably not. But let's talk about titration. So, before we look at the curve and whatever, I just want to make sure that you guys understand what titration is. But basically, titration is where you have a solution, where you have an unknown concentration. So you have an unknown molarity, either of an acid or a base. Okay, but it looks like in this question, it's going to be a base. Okay, because you have a methylamine, which is a base. Okay, and what you do is you put in the opposite of that solution. So the opposite of a base is an acid, right? So what you do is you slowly add acid into the base, and then you use something called an indicator. And when the moles of acid is equal to the moles of base, the indicator changes the color of the solution. Okay? What you're doing is you're adding the acid to the base, and when the color changes, that allows you to figure out how much base there was inside of that solution. Okay? Now, the color change happens right here. If you guys remember, on this titration curve, if you guys notice, it tells you how the pH changes as you add acid. So as you add acid, you guys can see the pH goes down, which makes sense, right? Because acidic is lower. And this sharp drop right here, this is called the equivalence point. Okay? And the equivalence point is where, or the middle of the equivalence point is where the moles of acid is perfectly equal to the moles of the base. Okay? So this should be a review, but if titration was a little bit hard to learn on your own with the video, because I wasn't here, because I hate you all, then this just our little recap, okay? Alright, so that is the basics of titration. And then now we can use this problem to figure out some information about what's going on. So it tells you that you're adding 1 molarity of HCl. Is HCl acid or base? Acid. What kind of acid? Strong. Oh, you guys are great. Okay. And then it tells you that you got 20 milliliters of your methylamine, which is a weak base. Okay, and if you watch Breaking Bad, that term should be familiar. That's what they use to make meth. Okay, methylamine. Okay, and this is going to be your base. And it tells you that it accepts a single proton, which means it's monoprotic, so it's just going to be just 1-to-1 ratio between them. Okay, and then it gives you this curve. All right, so before we do anything, what we can do is, using this titration curve, we can figure out how much base there is. Okay, so how much base? Okay, we can figure that out using this curve. Okay, we said that the equivalence point is where the moles of acid equals the moles of base. Using this chart, how much acid did I have to add to get the equal number of base? Yeah, 15 milliliters. So that means that in order to get to equivalence point, that means that you added 15 milliliters of acid. Okay? So far, so good? Okay. So, equivalence points is where the moles of acid is equal to the moles of base. So using this information right here, you can calculate the moles of base, because you can now calculate the moles of acid. So let me give you guys a minute to do that. If you remember, the molarity formula is molarity equals moles divided by liters. I want you to figure out how many moles of acid there are, and that's going to equal the moles of base you have in your solution that you're titrating. So take a minute to find the moles. All right, guys, so hopefully the math wasn't too hard. It's just 1 times the volume. You just needed to make sure to convert it to liters. So it should be 0.015 moles. Everybody good with that?
Yeah.
Okay. So I know that we calculated from the numbers for the acid, but we said at equivalence point, it is the moles of base as well. So you have 0.015 moles of your base. And let me scroll down a little bit. The question is asking, what's the concentration of the base? Well, we can find concentration using the molarity formula again. Molarity equals moles divided by liters, but this time we're talking about the base. So that means it's going to be 0.015 moles divided by 20 milliliters. So 0.02 liters. Okay, so let me give you a minute to finish copying that down. Oops. Okay, you should get 0.75. The other half of titration, it actually has to do with halfway equivalence point, if you guys remember that. We talked about the end of the unit, and it was also on your test. It has to do with like pKa, pKb, and things like that. So let me just pull this off the screen real quick and show you. The next question actually has to do with the same curve, and it's asking what's the approximate pKb for methylamine. Okay, pKb. All right, so pKb is it's kind of like pH, but instead of using the hydrogen concentration, you use the Ka, which is the ratio between the acid and the conjugate. So we're going to look at this curve again, and I'm going to show you guys how to find the pKb. All right, so let's talk about the next concept, the other half concept that we haven't talked about. So if you guys remember, at the beginning of the titration curve, okay, in this problem, we are adding acid to base, right? So before you add, when you are at 0 milliliters of acid, what is the only thing that is inside of your container? Yeah, so this spot right here, 0 point, is going to be when you only have base. Okay, so base only. Okay, which is pretty self-explanatory, right? And then we talked about equivalence point right here. So I'm going to call it EQ point. And equivalence point is where you have an equal number of acid and base, or equal amount. Okay. All right, let's go to the other extreme before we fill in the gaps. But this other end right here, this is where the pH stops changing. So this is basically us saying once you get to this point, you have an equal number, and at the very end, you only have acid, because what you're doing is basically you added enough acid to neutralize the base, and you're just adding more acid on top of that. So it's just acid. Okay, we typically don't talk about this point right here just because it's boring. It's the end of the experiment's already over. But just note, at the end of a titration curve, it flattens out because it's only what you're adding. Okay, so you can kind of see what it's going to be like. So let's talk about this position right here. So here, what do you think you're going to have more of? Yeah, you're going to have more acid than you have base, right? So here, this section right here, you're going to have more acid than base. Okay, and it'll be from equivalence point to this flattening out point. Okay, we also typically don't talk about this section right here because it's also very boring. You're pretty much past the point that's important, because once you get to equivalent point, you can figure out the concentration of the base. So you found it already, no need to put more acid in. All right, so this section right here is the section that is interesting and we talk about more. Okay, so what happens is when you have your base, you start adding your acid, right? And what happens is the acid starts to react with your base. So usually it'll be something like this, okay? And so when acid and base react, what is the first type of compound that gets made? Water, yeah, water, and the other one is? Salt, yeah, you make your salt, great. All right, so that is what happens. But what happens is oftentimes the salt is an ionic compound, right? So the ionic compound stays dissolved inside of the solution. And so you're going to have a cation and you're going to have an anion. Okay. Okay. So once you start adding acid to your base, what's going to happen in this first section right here, you're still going to have your base because you haven't completely neutralized it, but you will actually have more base than the ion, and that's called your conjugate acid. Okay, so you will have more base than your conjugate acid. Okay, but what happens is halfway to equivalence point, so this looks about 15, so halfway would be about 7.5. Halfway through though, okay, this is also an important point. This is the other important thing in titration they talk about. This is called the 1/2 equivalence point. So I'm going to write half equivalence point. And this section is significant because this is where your base is equal to your conjugate acid. Okay? And then beyond the halfway equivalence point until the equivalence point, you are going to have more conjugate acid than you're going to have base. Okay. So that's the other section that's important for titration, this right here, this halfway equivalence point information. So as you add acid, it starts to neutralize the base. So the base starts disappearing, which is why the pH goes down. But the first half, you're going to have more base still than the thing that got, than the neutralization. But at a certain point, you're going to start having less base than that. And that flipping area is called the halfway equivalence point. And this halfway equivalence point is important because, okay, the pH at the halfway equivalence point is exactly equal to the pKa. Okay, and also the pOH is equal to the pKb. Again, these represent the ratios between the acid and their conjugates. So if you guys remember, the question is asking you, what is the pKb for your base? Okay, so to find the pKb, we need to find the pOH. Okay, at halfway equivalence point. Okay, so a lot of people might be very tempted. You look at the graph and you're like, hey, halfway equivalence point, that's about 10.5, right? And then they put 10.5, but that is wrong. Why is 10.5 wrong?
Because like the equivalence point is at 15.
It is at 15, but we're still looking at the we're looking at the POH at halfway equivalence point. If you look at the graph, what are we measuring here? pH. We don't want pH for PKB. We want POH. Okay, so be very careful of these graphs. They'll put one measurement that's similar, but is not exactly what they're looking for. So we have pH. So the pH at halfway equivalence point is about 10.5. Yeah, 14 minus 10.5 to get POH will be 3.5. Okay, and that's going to be your POH, and that is also your PKB. So your answer will be 3.5. Okay, so a lot of little tricks. Okay, so let me repeat that just because I went a little fast at the end. Okay, so PKB is going to be the POH at halfway equivalence point. Okay, that part good?
Yeah.
Okay, if we look at the graph though, it is pH. So we have to turn pH into POH. So at halfway equivalence point, the pH is 10.5. To turn pH into POH, we do 14 minus the pH, and that'll give us 3.5. So the POH at this point is 3.5, and that is a PKB. So your answer will be 3.5. My bad, guys. I am not focused right now. Okay, so if you guys remember, does anyone remember what a buffer is?
When the reaction starts slowing down.
Yeah, basically a buffer is, it's going to be a here, let me yeah, it's a compound that resists pH change. So if you need to write that down, you can. But basically it resists change. Okay, so buffering region is basically which region of the titration is resisting pH change. So if we look at our curve right here, what is the shape of a graph that is going to resist pH change?
The bottom.
So there's going to be, it is in the bottom because if you look at it right here, what's the shape right here? It's flat, right? And if it's flat, the pH is not changing. If you're resisting pH, you are not changing pH. So this is one section, but what's the other flat section? Yeah, right here. Okay, and so this right here is actually going to be your buffer region. Okay, and the reason why it's this one and not this one is because, remember what we said earlier, what's the only thing that is existing in this flat area? It's all acid. So this is not a buffer because a buffer is not just all acid. It's going to be an acid or base and its conjugate salt, or a conjugate, or sorry, a salt with its conjugate. So this right here is the buffer region. And so if you look at it right here, it looks like it's about, I don't know, right here, underneath 5, right? So it's somewhere less than 5, and then it stops somewhere before 15, right? So we just look for something that fits that criteria. Yeah, so it should be B. Okay, don't need the exact numbers, just but if you can get that little range, then you can just very easily find what the correct answer will be. Yes. Okay, so we are comparing the pH of a weak base and strong base on a titration curve. So let's start with initial, because I think initial is the easiest. So between a weak base and a strong base, which one is more basic?
Strong
Yeah,
base.
obviously a strong base is more basic, right? And if something is more basic, does the pH go up or does it go down? It goes up, so that helps you a lot, right? You drop half the options already. So it has to be higher initially because you have a strong base now. So it's not going to be A, it's not going to be C. Okay, so just by knowing that a strong base is stronger, you can get half the answers. Okay. All right, let's move on. Now, equivalence point might be the one where you're like, ooh, I don't really know about that. So what we're going to do is we're actually going to skip this one, and we're going to go to ending pH because I think that makes things a lot easier. So if you guys remember, let's go back to the titration curve. At the end, what is the only thing left over?
Acid.
Acid. Now, you're still adding the same acid, right? So at the end, since you're adding the same acid and you only have acid left, is the pH going to be same or lower?
Same.
It's going to be the same. So your answer is going to be B.
I think we're passing.
You're going to pass all fives?
Yeah, all five.
Dude, all five. Let's go.
All fives in the front row.
My God, you guys will officially be my best class ever.
Yay.
I will tell legends of you guys.
Dream big.
Yeah, they didn't. Basically, they didn't even need me. I was holding them back. All right, so yeah, that's how you get that one. Also, equivalence point also makes sense that it's higher because if you think about it, if you have a strong base, you start higher, so that means your equivalence is also gonna get pulled up with it. Yeah.
Does that mean like the buffer region like increases? It's like there's more like resistance.
No, it's actually gonna be less resistance. It's gonna be more flat, or sorry, not flat, slanted.
Okay.
And if you want to see an example of that chart, it's gonna be in the workbook. Yeah, because if you go back to it, it's actually not gonna buffer, because if you remember, the definition of a buffer is going to be the base, and it's gonna be a salt with its conjugate. Okay, the problem with sodium hydroxide is a strong base, right? So NaOH, it's the conjugate cation is Na. It's not gonna want to form anything. It's not gonna form a salt. Yeah. So yeah, that one's a little bit strong base is gonna not have that flat region. Yeah.
So why was like the start? Why was it a higher?
Yeah, starts higher because it's a strong base. So if you remember the definition of a strong base is 100% dissociation, right? So that means that if you have NaOH, hey guys, all of the OHs are gonna go into the solution, which is gonna push the pH up, right? But methylamine is weak, so it's incomplete dissociation. So it's basically not gonna produce the same amount of OH in solution. Yeah, that's why. Alrighty. Last one. Okay, number 7. Alright, so we talked about this a long time ago, I think before winter, right after Thanksgiving break. So let's go through this one together. So you have a formate, which is right here. This is actually not one of the ones you need to memorize, so don't worry. And then it gives you a label for each bond. So we're going to zoom in, and let's take a look at what the bond order is. Now, bond order, if you guys remember from a long time ago, has to do with if it's a single, a double, or a triple bond. Okay. Obviously, a single is going to be bond order 1. Double is going to be bond order 2, so on and so forth. Okay. But there is one other thing that goes into bond order, and it's going to be resonance. If you remember, resonance means you can draw the picture multiple ways, right? So there's a double bond here, but we can also draw the picture like this, with a double bond to the lower oxygen. And that's also equally right. So that means that in reality, there's going to be these dotted lines. And anyone remember what these are called? What type of bonds? Half bonds. Yeah, so this will be 1.5 bonds. Okay, so if you have resonance, you can have 1.5 bonds. Okay, and also 1.33 if it's shared between 3 elements. Okay, so I kind of gave the answer to you guys, but if you look at this structure, can you make resonance?
Yeah.
Yes. So let's look at X. Okay, this is a single. Can it go into resonance? No, it cannot. So what does X have to be? 1. X has to be 1. But Y and Z can both be double or single. It can be resonant. So these guys will be 1.5. So your answer is going to be C. Okay. So the key for this one is identifying, hey, I can get a resonance structure.
I have amazing.